Can a helium ion produce the exact same spectral line as hydrogen? Let's find out.
Here's our approach. First, we verify statement 1, whether electric discharge through hydrogen really does produce discrete spectral frequencies. Then, we tackle statement 2 using the Rydberg frequency formula. We'll compute the second Balmer line from helium ion and the first Lyman line from hydrogen. If both give the same result, statement 2 is true. The key insight is how the z-squared factor works in that formula. Statement 1 is true. Electric discharge breaks hydrogen molecules into atoms, and electrons get excited to higher energy levels. When they fall back down, they release energy as photons. Because atomic energy levels are quantized, only specific discrete frequencies can be emitted. This is the very origin of line spectra. Statement 1 is correct. For statement 2, we use the Rydberg formula. Frequency equals R times Z squared times C times the quantity 1 over N1 squared minus 1 over N2 squared. Z is the atomic number, and N1 and N2 are the quantum numbers of the two levels involved. For He plus, Z equals 2, the second Balmer line means N1 equals 2 and N2 equals 4. We get 4 times Rc times 1/4 minus 1/16. That's 4 Rc times 3 over 16, which beautifully simplifies to 3 Rc over 4. For hydrogen, Z equals 1, the first Lyman line, N1 equals 1, N2 equals 2. Frequency equals Rc times 1 minus 1/4, giving us 3 Rc over 4, identical to He plus. Both frequencies are exactly 3 Rc over 4. Statement 2 is also true. With both statements verified, the answer is option 3. Both statement 1 and statement 2 are true. 4 pressure-volume graphs, same gas, same endpoints. Which process squeezes out the maximum work? The answer is a classic JEE trap. Here's our approach. The key principle is this: work done by a gas equals the area under the PV curve. So we need to find which graph has the largest area under its expansion path. We'll recall what that area represents. Then we'll compare each graph. The winner will be the path that stays highest in pressure throughout the entire expansion. The formula is simple. Work equals the integral of pressure times change in volume. Geometrically, that's the area between the curve and the volume axis. More area means more work. So the graph with the tallest, graph 2, shows a smooth, curved expansion. This is a reversible, quasi-static process. At every tiny step, the gas pushes against the maximum possible external pressure. Because the curve stays high up in pressure, as volume increases, it sweeps out the largest area beneath it. This is why reversible expansion gives maximum work. It's a fundamental thermodynamic principle. Graph 1 is the classic trap. Yes, the expansion follows the same smooth curve, but then the gas compresses back at low constant pressure. That compression gives back work to the surroundings. The net work is just the enclosed area between the two paths, which is much smaller. Graph 3 shows a closed loop. Its net work is only the lens-shaped enclosed area, smaller still. Graph 4 shows expansion at constant high pressure, but it covers a completely different volume range and represents a different process altogether, so it can't be directly compared. The smooth reversible expansion has the maximum area under the curve, and therefore the maximum work done. Remember, for any expansion between the same two states, the reversible path always wins. Key takeaway: maximum work means reversible process, which means smooth curve, which means maximum area under the PV graph. Coordination chemistry in JEE loves to test one thing. Can you quickly figure out how many unpaired electrons a complex actually has? In this question, we need to judge two statements about magnetic properties of nickel and manganese complexes. First, we'll identify the metal oxidation state and d-electron count for each complex in statement 1. Then we count unpaired electrons using crystal field theory to determine which has the maximum. For statement 2, we'll examine 3 nickel complexes, checking their geometry and field strength to decide which are diamagnetic. Starting with statement 1, copper 2 plus is D9. 1 unpaired electron. Both nickel 2 plus complexes are D8 in octahedral field, which always gives 2 unpaired no matter the field strength. But manganese 2 plus with water ligands is the key. Water is weak field, so manganese stays high spin with 5 unpaired electrons, the maximum by far. Statement 1 is true. Now statement 2, NiKl4 2- is tetrahedral with weak field chloride. Nickel 2 plus here is D8 with 2 unpaired electrons, so it's paramagnetic. NiCO4 has nickel in zero oxidation state, giving D10, fully paired diamagnetic. And NiCN4 2- is square planar with strong field cyanide, forcing D8 to pair completely. Also diamagnetic. The first 2 pairs each contain NiCl4 2-, which is paramagnetic, so those pairs are out. Only the pair containing NiCO4 and NiCN4 2- are both diamagnetic. That's just 1 pair, not 2. Statement 2 is false. The answer is option 1. Statement I is true. Statement 2 is false. 14 grams of calcium reacts with excess hydrochloric acid. We need to find which statement about this reaction is incorrect. Here's our approach. First, we write the balanced equation for calcium reacting with HCl. Then we calculate the moles of calcium. Since HCl is in excess, calcium is the limiting reagent. We verify each statement about hydrogen gas produced. Finally, we check the mass of calcium chloride, and that's where the trap is hiding. The balanced reaction is calcium plus 2 moles of hydrochloric acid, giving calcium chloride and hydrogen gas. Notice the 1-to-1 molar ratio between calcium and hydrogen. Now, the moles of calcium. 14 grams divided by the molar mass of 40 gives us exactly 0.35 moles. Since HCl is in excess, calcium is the limiting reagent. Statement 2 is correct. For statement 1, 1 mole of calcium produces 1 mole of hydrogen, so we get 0.35 moles of hydrogen gas. Correct. Statement 4 says 7.84 liters. At STP, 1 mole of gas is 22.4 liters, so 0.35 moles gives exactly 7.84 liters, also correct. Here's the key move. Statement 3 claims 33.3 grams of calcium chloride is produced. Let's check. The molar mass of calcium chloride is 40 plus 2 times 35.5, because there are 2 chlorine atoms. That gives 111 grams per mole. The actual mass is 0.35 times 111, which is 38.85 grams. Statement 3 is wrong. The trap is forgetting that calcium chloride has 2 chlorine atoms. Using just 1 chlorine gives 75 instead of 111, leading to the wrong answer. Always count your atoms carefully. Here's a question with a clever trap. Compound P passes the iodoform test, but fails Tollens. Then, acid treatment transforms it into Q, which passes both tests. Something is being hidden in P's structure. Here's our approach. First, we'll decode what each test actually detects. Iodoform is specific to methyl ketones, while Tollens requires a free aldehyde. Then we'll use those constraints to eliminate wrong options. The key move is recognizing that P's aldehyde group is protected as an acetal, which is why Tollens doesn't fire. Finally, we verify that acid hydrolysis unmasks the aldehyde in Q. P gives positive iodoform, which tells us it has a methyl ketone group. That carbon-carbon double bond with a methyl attached. But P fails Tollens test, meaning there's no free aldehyde present. So P hides its aldehyde somewhere. Now look at option 2. It has a free formal group right at the start of the chain, so it would already give positive Tollens. That's eliminated. Option 1 gives butanedione on acid treatment, a diketone with no aldehyde. So, Q would still fail Tollens, also out. Option 3 is the key. It has a methyl ketone at one end and a dimethyl acetal at the other, meaning the aldehyde group is masked as a carbon with two methoxy groups. That's exactly why toluenes is negative. But dilute acid breaks the acetal linkage and releases the free aldehyde.
So, Q becomes 3-oxobutanol. It has a methyl ketone for positive iodoform and a free aldehyde for positive toluenes.
Both conditions satisfied. The correct structure of P is option 3, the acetal-protected ketoaldehyde. A hydrocarbon with formula C4H8 reacts with HCl to give an optically active product. Which structure makes that possible? Here's our approach. First, we'll use the degree of unsaturation to confirm P is an alkene. Then we'll apply Markovnikov's rule to find Q. The key move is checking which isomer creates a chiral center when HCl adds across. Finally, we'll trace the amine to alcohol conversion. C4H8 has exactly 1 degree of unsaturation, so P is an alkene. The only C4 alkene where HCl addition gives a chiral chloride is but-2-ene. Adding HCl by Markovnikov's rule places chlorine on carbon 2, which ends up bonded to 4 different groups. Now the next step is to understand the optical activity of Q.
That carbon 2 in 2-chlorobutane carries a hydrogen, a methyl group, an ethyl group, and chlorine. All 4 are different. This makes it a stereocenter. So Q is 2-chlorobutane, and it's optically active because of this one chiral carbon. Q reacts with 1 mole of ammonia by substitution. Chlorine leaves, and the amino group takes its place. This gives R,
which is 2-aminobutane, a primary amine with formula C4H11N. Notice the chiral center is preserved. Now for the diazotization. R reacts with sodium nitrite and HCl at 0 degrees to form an aliphatic diazonium salt. Unlike aryl diazonium salts, aliphatic ones are completely unstable. They instantly lose nitrogen gas, generating a carbocation. Water captures that carbocation immediately, giving S, which is 2-butanol. The OH ends up on the same carbon as the original amine. So, P is but-2-ene, Q is 2-chlorobutane, R is 2-aminobutane, and S is 2-butanol. That's option 2. 5 statements about amino acids. Which ones are actually correct? Let's check each one before the exam tricks us. Here's our approach. First, we'll check whether arginine and tryptophan count as essential amino acids. Then we'll look at histidine's ring, proline's ring size, and whether glycine has a chiral center. We'll unmask a classic side chain swap involving cysteine. Statement A. Arginine and tryptophan as essential amino acids. Essential means the body cannot make them. They must come from food. Both arginine and tryptophan are on the standard essential amino acid list. Statement A is correct. Statement B claims histidine has no heterocyclic ring, but histidine's side chain contains an imidazole ring, a 5-membered ring with 2 nitrogen atoms embedded inside it. Any ring with a non-carbon atom is by definition heterocyclic. Statement B is false. Statement C says proline is a 6-membered cyclic amino acid. Let's count the atoms in proline's ring. 1 nitrogen plus 4 carbons. That's 5 atoms total. The ring is called pyrrolidine, and it is 5-membered, not 6. Statement C is false. Statement D, glycine has no chiral center. A chiral center needs 4 different groups on the alpha carbon. Glycine's alpha carbon carries 2 identical hydrogen atoms, breaking that requirement. So glycine is the only naturally occurring amino acid with no chirality. Statement D is correct. Statement E gives cysteine the side chain methyl sulfide -CH2-CH2, but that structure belongs to methionine, not cysteine. Cysteine's actual side chain is simply CH2-SH, a thiol group. This is the classic JEE trap. Cysteine and methionine both contain sulfur, but in completely different arrangements. Statement E is false, so only A and D are correct. The answer is option 3, A and D only. Remember, glycine is achiral, and cysteine carries a thiol, not a thioether. 2 mysterious elements. 2 compounds, and a boiling point clue that reveals both atomic masses at once. Here's our approach. We're given that both compounds are non-volatile and non-ionizable, which means boiling point elevation applies directly, with no dissociation correction. We'll use the elevation formula to find the molar mass of each compound separately. Then we'll subtract the two results to isolate Q, and back substitute to find P. The key formula is boiling point elevation equals Kb times molality. Since molality is moles of solute per kilogram of solvent, we can rearrange to get molar mass equals Kb times the solute mass, divided by the elevation times the solvent mass in kilograms. For compound PQ, 1 gram dissolved in 50 grams of solvent with an elevation of 1.176 Kelvin, we get a molar mass of about 85 grams per mole. That's our first anchor point. The smaller elevation of 0.689 Kelvin means a heavier molecule. Running the same formula gives a molar mass of 145 grams per mole. Notice PQ2 is heavier than PQ, which makes sense. It carries an extra Q atom. Here's the key insight. Going from PQ to PQ2 adds exactly 1 Q atom, so the difference in molar masses is the mass of Q. 145 minus 85 gives us Q equals 60 grams per mole. Then P equals 85 minus 60, which is 25 grams per mole. The answer is option 2. P is 25, Q is 60. Notice that option 3 lists 65 and 145. Those are the compound masses, not the elements. Classic JEE trap. We need to identify compound A, which gives decalin on hydrogenation and specific dicarboxylic acids on oxidation. Let's work through the clues. Here's our approach. First, we'll use the hydrogenation data to find how many double bonds A has. Then we'll analyze the oxidation products to locate exactly where those bonds sit. Finally, we'll match to the correct option. Since A plus 2 moles of hydrogen gives decalin, A must have exactly 2 carbon-carbon double bonds beyond its ring structure. That narrows it to a partially unsaturated bicyclic compound. Now for the oxidation clue. Potassium permanganate with heat cleaves double bonds, converting each carbon to a carboxylic acid group. The products are cyclohexane dicarboxylic acid and oxalic acid. Here's the key insight. The intact cyclohexane ring tells us one ring was already saturated. The oxalic acid, a 2-carbon fragment, means both double bonds sat in the other ring. This points directly to a structure with 2 double bonds confined to one ring of the naphthalene skeleton. Checking option 1. It has exactly 2 double bonds in one ring. The other ring is saturated. Hydrogenation gives decalin. Oxidation gives the right products. That's our answer, option 1. Seven molecules, 2 bold claims. How many are truly tetrahedral? And do all 4 here have an incomplete octet? Here's our approach. First, we'll go through each species in statement 1 and check whether it's genuinely tetrahedral, using VSEPR for the main group molecules and ligand field strength for the transition metal complexes. Then, we'll verify statement 2 by counting electrons around each central atom. The key move is spotting the nickel contrast. Let's start with sulfur tetrafluoride and selenium tetrafluoride. Both sulfur and selenium have 4 bond pairs plus 1 lone pair. That's 5 electron domains, giving a seesaw shape. 4 bonds doesn't automatically mean tetrahedral. The lone pair changes everything. Ammonium ion is the clean case. Nitrogen forms 4 bonds to hydrogen with no lone pairs left. Perfect tetrahedral symmetry. That's our first confirmed tetrahedral species. Now the interesting one, the 2 nickel complexes. Both have nickel 2+, which is a D8 ion. In tetrachloronickelate, chloride is a weak field ligand, so the splitting is small and nickel stays tetrahedral. That's our second tetrahedral species. But in the cyanide complex, cyanide is a strong field ligand. It forces the electrons to pair up, giving square planar geometry instead. That's 6 electron domains with the lone pairs going trans to each other, giving square planar. And platinum 2 plus is a heavy 5D metal. All its complexes are square planar, regardless of the ligand. So how many are tetrahedral? Just 2. Ammonium and tetrachloronickelate. Statement 1 claims 3. That's wrong, which makes statement 1 false. Now statement 2. Nitrogen dioxide has an odd number of electrons. Nitrogen never completes its octet. Beryllium in beryllium dihydride has only 4 electrons around it. Boron and aluminium in their trichlorides each have only 6 electrons. All 4 have incomplete octets. Statement 2 is true. The answer is option 4. Statement 1 is false. Statement 2 is true.
Statement 2 is true. 4 periodic property trends.
3 are correct, and 1 is a classic JEE trap hiding in plain sight. Here's our approach. First, we'll verify the first ionization energy trend for fluorine, phosphorus, sulfur, and boron. Then we check electron affinity for chlorine, fluorine, sulfur, and phosphorus. Next, we examine metallic character. And finally, the basic character of metal oxides. The key moves are 2 famous anomalies that JEE loves to test. Option A says, first ionization energy follows F greater than P greater than S greater than B. Fluorine has one of the highest ionization energies of all elements. Now here's the critical anomaly. Phosphorus actually beats sulfur. Why? Phosphorus has a half-filled 3p subshell, which is extra stable because of exchange energy. Sulfur has one paired electron in 3p that experiences repulsion, making it easier to remove. So this trend is correct. Option B says electron affinity follows chlorine greater than fluorine greater than sulfur greater than phosphorus. The counterintuitive part, chlorine beats fluorine, despite fluorine being more electronegative. Fluorine's atomic radius is extremely small, so adding an extra electron into that crowded 2p orbital causes severe electron-electron repulsion. Chlorine is larger and accommodates the new electron much more comfortably. Phosphorus has the lowest electron affinity because its stable half-filled 3p resists gaining an electron. This trend is also correct. Option C says metallic character goes K greater than aluminum, greater than magnesium, greater than B. Here's the trap. Magnesium and aluminum are both in period 3. Moving left to right across a period, metallic character decreases. So magnesium in group 2 is more metallic than aluminum in group 13. The correct order should be K, then magnesium, then aluminum, then B. Option C has magnesium and aluminum swapped. It's wrong. Option D says basic character of metal oxides follows K2O greater than Na2O greater than MgO greater than Al2O3. Basic character of a metal oxide tracks the metallic character of its metal. Potassium is more metallic than sodium, so K2O is more basic. Moving across period 3 from sodium to magnesium to aluminum, metallic character and basic character both decrease. Al2O3 is actually amphoteric. This trend is correct. So statements A, B, and D are correct. Option C fails because magnesium is more metallic than aluminum. The answer is option 1, A, B, and D only. Most students see a positive delta G standard here and immediately think, no reaction. That's the trap. Here's our approach. We have a graph of Gibbs free energy versus the fraction of N2O4 that dissociates. First, we'll read delta G standard directly from the graph as the height difference between the two pure endpoints. Then, we'll locate the equilibrium minimum. Finally, we'll evaluate all 5 statements one by one using the graph values. The key move is this. Delta G standard equals the free energy of pure products minus pure reactants. On the graph, point B is pure NO2 and point A is pure N2O4. B sits higher than A by 5.4 kilojoules per mole. So, delta G standard equals positive 5.4. Statement A says negative. That's immediately wrong. Now here's the big trap. Statement B claims that because delta G standard is positive, N2O4 won't dissociate at all. But positive delta G standard only tells us about the standard state. The curve has a minimum at point E, between A and B. The system always moves toward that minimum, so dissociation definitely occurs. Statement C says the reverse reaction goes to completion. Going to completion would mean the system stops at pure N2O4, which is point A. But our equilibrium minimum is at E, not A. So the reverse reaction stops at E, not complete. Now the two correct ones. Statement D. When we start from pure N2O4 and reach equilibrium, the free energy drops by 0.84 kilojoules per mole. That's exactly the depth of point E below point A on the graph. The system loses that much energy, so delta G equals negative 0.84. Statement D is correct. Starting from pure NO2 and reaching equilibrium, point B is 5.4 above A, and E is 0.84 below A. So E is 6.24 below B. Delta G equals negative 6.24 kilojoules per mole. Statement E is also correct. So the correct statements are D and E, option 1. The key lesson: equilibrium is where G is minimum, not where delta G standard is 0. 3 reactions, 3 unknowns, A, B, and X. Can you identify all 3 before we work through them? Here's our approach. First, we'll look at reaction 1 as a simple precipitation to pin down A. Then we'll use A in reaction 2, where the amphoteric nature of lead reveals B. Finally, we'll balance atoms in reaction 3 to find X as an acetate complex salt. Let's work through each step. In reaction 1, lead chloride meets potassium chromate in hot solution. Lead 2+ combines with chromate ions to form lead chromate, a classic yellow precipitate with an extremely low solubility. The potassium and chloride ions pair off as potassium chloride and stay dissolved. So A equals PbCrO4. Now for B. Lead chromate reacts reversibly with sodium hydroxide. Here's the key insight. Lead is amphoteric, which means it can behave like a metal and dissolve in strong base. In excess NaOH, the chromate ion is released as sodium chromate, while lead 2+ picks up 4 hydroxide groups. This forms the tetrahydroxoplumbate complex, because lead 2+ prefers a coordination number of 4 in alkaline solution. B equals Na2 PbOH4. For X, we count ions. The sulfate from lead sulfate pairs with 2 ammonium ions to give the ammonium sulfate product we see on the right. That accounts for half the ammonium acetate. The remaining lead 2+ and 4 acetate ions combine with 2 more ammonium ions to form the acetate complex salt. X equals ammonium tetricus acetoplumbate 2. So our final answer, A is PbCrO4, B is the tetrahydroxoplumbate complex, X is the acetate complex. The answer is option 3. 3 reactions, 3 unknowns, A, B, and X. Can you identify all 3 before we work through them? Here's our approach. First, we'll look at reaction 1 as a simple precipitation to pin down A. Then we'll use A in reaction 2, where the amphoteric nature of lead reveals B. Finally, we'll balance atoms in reaction 3 to find X as an acetate complex salt. Let's work through each step. In reaction 1, lead chloride meets potassium chromate in hot solution. Lead 2+ combines with chromate ions to form lead chromate, a classic yellow precipitate with an extremely low solubility. The potassium and chloride ions pair off as potassium chloride and stay dissolved. So A equals PbCrO4. Now for B. Lead chromate reacts reversibly with sodium hydroxide. Here's the key insight. Lead is amphoteric, which means it can behave like a metal and dissolve in strong base. In excess NaOH, the chromate ion is released as sodium chromate. While lead 2+ picks up 4 hydroxide groups, this forms the tetrahydroxoplumbate complex, because lead 2+ prefers a coordination number of 4 in alkaline solution. B equals Na2 PbOH4. For X, we count ions. The sulfate from lead sulfate pairs with 2 ammonium ions to give the ammonium sulfate product we see on the right. That accounts for half the ammonium acetate. The remaining lead 2+ and 4 acetate ions combine with 2 more ammonium ions to form the acetate complex salt. X equals ammonium tetricus acetato-plumbate 2. So our final answer, A, is PbCrO4. B is the tetrahydroxyplumbate complex. X is the acetate complex. When we burn an organic compound in the Carius method, all the sulfur it contains gets converted into barium sulfate precipitate. So measuring that precipitate lets us work backwards to find exactly how much sulfur was present. Here's our approach. First, we use the key principle of Carius method. Every mole of sulfur produces exactly 1 mole of barium sulfate. Then, from the mass and molar mass of barium sulfate, we find the moles formed. Since the molar ratio is 1:1, that equals the moles of sulfur. Finally, we convert to mass and apply the percentage formula. The 1:1 relationship is everything here. We're given 0.75 grams of organic compound, 1.2 grams of barium sulfate formed. Molar mass of barium sulfate is 233, and molar mass of sulfur is 32. Now moles of barium sulfate equals 1.2 divided by 233. And since every mole of barium sulfate came from exactly 1 mole of sulfur, moles of sulfur is the same. So mass of sulfur equals this number times 32. That works out to 38.4 over 233 grams. Applying the percentage formula, 32 times 1.2 divided by 233 times 0.75, all times 100. That's 38.4 over 174.75 times 100. And we get 21.97%. So the answer is option 1, 21.97%. Remember the golden rule of Carius method. Mass of sulfur and mass of barium sulfate are always in a fixed ratio of 32 to 233. 4 pairs of oxides. We need to find how many pairs have both oxides amphoteric. Here's our approach. First, we'll define what makes an oxide amphoteric. It must react with both acids and bases. Then we'll screen each of the 4 pairs one by one. The key move is catching the PbO2 trap. Finally, we'll verify all 4 claims about BF3. Let's go. Start with the first pair, silicon dioxide and carbon dioxide. Both are nonmetal oxides, purely acidic. They react with bases, but not with acids in any base-like way. That pair is out. Now the tin pair, tin 2 oxide and tin 4 oxide. Both react with hydrochloric acid and with sodium hydroxide. Both amphoteric. That pair qualifies. Now the critical pair, lead 2 oxide and lead 4 oxide. PbO is amphoteric. It dissolves in both acids and bases. But PbO2 is different. In the +4 oxidation state, lead dioxide is a powerful oxidizing agent. Its reaction with acids is an oxidation reaction, not neutralization.
So PbO2 does not qualify as amphoteric. That pair is out. The germanium pair passes easily. GeO and GeO2 both react with acids and with bases. Both are amphoteric. That's our second qualifying pair. So the total count is 2, exactly what Statement 1 claims. Statement 1 is true.
Now, Statement 2 about BF3. Boron only forms 3 bonds, leaving just 6 electrons around it, so it is electron deficient. That empty orbital makes it a textbook Lewis acid. It readily accepts the lone pair from ammonia to form the BF3 ammonia adduct. And with sp2 hybridization, the geometry is trigonal planar. All 4 claims check out. Now let's reveal our answer. Both statements are true. The answer is option 2. The key insight: PbO2 oxidizes rather than neutralizes, breaking the pattern of its own group. A mystery hydrocarbon burns completely in oxygen. The leftover gas volumes hold a precise chemical fingerprint. Let's decode it. Here's our approach. First, we write the general combustion equation for any hydrocarbon. Then, since KOH dissolves carbon dioxide, the volume drop on KOH treatment tells us exactly how much CO2 formed. From that CO2 volume, we find the number of carbons. Finally, oxygen balance reveals the hydrogen count. Burning any hydrocarbon gives carbon dioxide and water. At 273 Kelvin, that's 0 degrees Celsius, water is liquid, so it's not counted. The 224 milliliter residual is purely CO2 plus leftover oxygen. We started with 80 milliliters of hydrocarbon and 264 milliliters of oxygen. KOH is a strong alkali that grabs carbon dioxide out of a gas mixture. Volume drops from 224 down to 64 milliliters, a fall of 160. So carbon dioxide is 160 milliliters, and the surviving 64 milliliters is all excess oxygen. Every molecule of the hydrocarbon produces X molecules of carbon dioxide. We burned 80 milliliters and got 160 milliliters of CO2, exactly double. So X equals 2. There are 2 carbon atoms per molecule. Now for hydrogen. Oxygen consumed equals 264 minus 64, that's 200 milliliters. Per molecule of hydrocarbon, the ratio is 2.5. Plugging X equals 2 into the stoichiometry equation, X plus Y over 4 equals 2.5, gives Y equals 2. Our hydrocarbon is C2H2, acetylene. Let's verify. Acetylene burns with exactly 200 of the 264 milliliters of oxygen, producing 160 of CO2 plus 64 excess. After KOH, exactly 64 milliliters. The molecular formula of R, C6H7N, is your master key here. That one formula lets you solve the entire chain backwards. Here's our approach. First, we'll decode compound R by analyzing C6H7N. Then we'll use the Hofmann-bromamide rearrangement to figure out what amide Q must be. Next, we'll confirm Q from its structure. We'll trace P from the ammonia reaction. The formula drives everything. Let's decode R. C6H7N has a degree of unsaturation of 4. That means a benzene ring. 6 carbons, 1 nitrogen, 7 hydrogens. That's aniline, a benzene ring with an amino group. This immediately eliminates options 1 and 3, since 4-methylaniline or 2-methylaniline would be C7H9N, not C6H7N. Now, the Hofmann-bromamide rearrangement. When an amide reacts with bromine and hot potassium hydroxide, the product is a primary amine with 1 fewer carbon than the amide. So if R is aniline with 6 carbons, Q must be a 7-carbon amide containing a phenyl group. A 7-carbon amide with a phenyl group, that's benzamide. Apply the Hofmann reaction to benzamide and you get aniline. Carbon count checks out perfectly. With Q as benzamide, tracing back to P is straightforward. Benzamide forms when benzoic acid reacts with aqueous ammonia under heating. The carboxylic acid converts to the amide via an ammonium salt intermediate. Benzoic acid gives benzamide. Benzamide gives aniline. That's option 2. C6H7N was the diagnostic clue all along, uniquely pointing to aniline and locking in the entire chain.
5 isomerism statements on the board. But which ones are actually correct? Most students get at least 2 of these wrong because they mix up the types. Here's our approach. We'll check each statement by applying its exact isomerism definition. Same molecular formula is just the entry ticket. What matters is what's different: the functional group, the alkyl distribution, the carbon skeleton, or the presence of a chiral center. Statement A. Propanol and propanone both have the molecular formula C3H6O. But propanol is an aldehyde, and propanone is a ketone. Completely different functional groups. Different functional group, same formula. That's textbook functional isomerism. Statement A is correct. Statement B, ethoxyethane and methoxypropane.
Both are ethers with formula C4H10O, so the functional group is the same. but the alkyl groups on either side of the oxygen are different. Ethyl-ethyl versus methyl-propyl. Same functional group, different alkyl distribution. That's metamerism. Statement B is correct. Statement C, but-2-ene and optical isomerism. But-2-ene has a carbon-carbon double bond, giving it cis and trans forms. That's geometric isomerism. For optical isomerism, we need a chiral center, a carbon with 4 different groups attached. But-2-ene has no such carbon. Statement C is wrong. Statement D, but-1-ene and but-2-ene as functional isomers. Both are alkenes with formula C4H8 and the same C double bond C functional group. The only difference is the position of that double bond, position 1 versus position 2. Same functional group, different position. These are positional isomers, not functional isomers. Statement D is wrong. Statement E, pentane and 2,2-dimethylpropane. Both are C5H12 alkanes.
But pentane is a straight 5-carbon chain, while 2,2-dimethylpropane is fully branched around a central carbon. Different carbon skeleton, same formula. That's chain isomerism. Statement E is correct. So statements A, B, and E are correct. The key takeaway: always apply the precise definition. Isomerism type depends on exactly what structural feature changes between the two compounds.
Paragraph 1. Hook, 0 seconds to 7 seconds. 17 words. Our approach, 8 seconds to 21 seconds. 33 words. Paragraph 3. Statement A, 22 seconds to 32 seconds. Paragraph 4. Statement B, 37 seconds to 53 seconds. 41 words. Paragraph 5. Statement C, 54 seconds to 68 seconds. 38 words. Paragraph 6. Statement D, 69 seconds to 83 seconds. Paragraph 7. Statement E, 84 seconds to 98 seconds. Hashtag 99, 911, 29 words. Total, 270 words, 108 seconds audio. 4 structures, same molecule, same atoms, same bonds. Only one charge arrangement is dangerously unstable. Which one and why? Here's our approach. First, we lock in the rules that decide resonance stability. Then, we map the formal charges in each of the 4 structures. The key move is spotting where adjacent positive charges appear. That is the fatal flaw. Finally, we identify the least stable structure. Resonance structures are more stable when they have more bonds, when negative charges sit on electronegative atoms like oxygen rather than carbon, and when there are fewer formal charges overall. But the real killer rule, adjacent like charges, meaning 2 positive charges right next to each other, makes a resonance structure extremely unstable. Now let's map the charges. Structures 1, 3, and 4 all have charges that are either alternating or well separated. Their negative charges also land on oxygen, which is favorable. Structure 2 is different, and that difference is decisive. In structure 2, 2 positive charges land on C1 and C2, directly adjacent carbons in the chain, with no negative charge between them. Like charges on neighboring atoms create maximum Coulombic repulsion. The system cannot lower its energy through resonance. Additionally, the negative charge in structure 2 sits on carbon, which is less electronegative than oxygen or nitrogen. So, structure 2 is the least stable resonance contributor. Adjacent positive charges are the fatal flaw. The answer is option 2. Remember, adjacent like charges equal instant destabilization. That is the pattern JEE tests here, and that is your exam weapon. What happens when a manganese compound cannot decide whether to oxidize or reduce? It does both. Here's our approach. First, we assign oxidation states to manganese in the reactant and all 4 product candidates. Then we apply the disproportionation concept, where one species simultaneously oxidizes and reduces. We balance the equation and eliminate the wrong options. In manganate ion, manganese is at oxidation state +6. Disproportionation means this same species acts as both oxidizing and reducing agent. Part gets oxidized to +7, forming permanganate ion. The other part gets reduced to +4, forming manganese dioxide. For electron balance, 2 permanganate ions form for every 1 MnO2. Here's the balanced equation in acidic medium. 3 manganate ions plus 4 protons give 2 permanganate ions, 1 MnO2, and 2 water molecules. Options 2, 3, and 4 are wrong. MnO needs manganese at +2, which is too strongly reduced, and Mn2O7 simply does not form in aqueous acidic conditions. So the answer is option 1, permanganate ion and manganese dioxide. Acidic medium drives manganate from +6 toward +7 above and +4 below simultaneously. 3 reactions, 3 unknowns, and a final compound that turns deep blue. Let's figure out exactly what's going on. Here's our approach. First, we'll identify product A from the classic chromal chloride test, a reaction every JEE student should recognize. Then we'll track A through hydrolysis to get B, a yellow chromate salt. We'll see how B reacts with hydrogen peroxide to form C, a special peroxo compound. Once we know C's structure, extracting X, Y, and Z is straightforward. The first reaction is the chromal chloride test. When sodium chloride is heated with potassium dichromate and concentrated sulfuric acid, the chloride ions get incorporated into the chromate framework, producing chromal chloride, a volatile, deep orange-red compound. This is product A. The sulfate salts and water on the right side confirm this perfectly. Now A reacts with sodium hydroxide. Chromal chloride has 2 chlorine atoms bonded to chromium. Base hydrolysis replaces those chlorines with hydroxide, converting the compound into sodium chromate, a bright yellow salt. Product B is sodium chromate, and the sodium chloride byproduct confirms our equation. Here's the key reaction. Sodium chromate in acidic conditions meets hydrogen peroxide. Instead of a simple oxidation, the hydrogen peroxide acts as a peroxo donor. Its oxygen-oxygen bond stays intact and coordinates to chromium. The result is chromium pentoxide, CrO5, which appears as a striking deep blue compound. Now, let's decode C's structure. CrO5 is actually CrO with 2 peroxo groups, written as CrO bracket O2 bracket sub 2. There's 1 terminal oxygen and 2 O2 square minus peroxo units. So X equals 2 peroxo groups, and Y, the total oxygen count, is 1 plus 4, giving us 5. Finally, the oxidation state of chromium. In a peroxo group, each oxygen sits at -1, not -2. So the 2 peroxo groups together contribute -4, and the terminal oxygen contributes -2. Since CrO5 is neutral, chromium must be +6, Z equals 6, so X plus Y plus Z equals 2 plus 5 plus 6, which gives us 13. That's the final integer answer for this question. A weak acid gives away very few ions. Its pH tells us the ion concentration. But how do we find the limiting molar conductivity without even knowing the acid's concentration? Here's our approach. First, we convert the electrogeometry into a cell constant. Then, we multiply by the measured conductance to get conductivity. Third, we extract H+ concentration from the pH. The elegant insight is that when we divide these two results, the unknown concentration cancels out completely. The cell has plates 1 square centimeter in area, 15 centimeters apart. In SI units, it's straightforward. The cell constant is 1500ths of a meter over 10 to the -4 square meters, giving 1500 per meter. Multiply conductance by the cell constant. 4 times 10 to the -5 times 1500. That gives conductivity of 0.06 Siemens per meter. Let's convert that pH to H+. pH equals 5 means H+ concentration is 10 to the -5 moles per liter. Converting to SI, that's 10 to the -2 moles per cubic meter. Here's the key move. For a weak acid, molar conductivity equals alpha times limiting molar conductivity, and H+ concentration equals alpha times C. Dividing through, alpha and C both cancel. Limiting molar conductivity equals conductivity divided by H plus concentration. Plugging in, 0.06 divided by 10 to the minus 2 equals exactly 6. The limiting molar conductivity is 6 Siemens meter squared per mole. One number in this thermodynamic data table is unknown, the heat of formation of B2. We're told the equilibrium constant at 500 Kelvin. The challenge is to use that information to track down the missing enthalpy value. Here's our approach. First, we'll calculate the entropy change for the reaction using the known entropy values in the table. Then, we'll convert the equilibrium constant into a standard Gibbs free energy using delta G equals negative 2.303 times R times T times the logarithm of K. Finally, we'll connect everything through the fundamental relation delta G equals delta H minus T delta S to solve for X. Let's start with the entropy change. Products minus reactants, 2 times the entropy of AB minus the entropy of A2 minus the entropy of B2. That gives us 444 minus 146 minus 280, which simplifies to 18 joules per Kelvin per mole. Now, we convert K to delta G naught. We know log K equals 2.2, T is 500 Kelvin, and R is 8.3 joules per Kelvin per mole. Plugging in, the result is approximately negative 21 kilojoules per mole. Notice how a large K gives us a strongly negative delta G. The reaction strongly favors products. Now express the enthalpy of reaction using Hess's law. 2 times the heat of formation of AB minus that of A2 minus X. That's 58 minus X kilojoules. Substitute into delta G equals delta H minus T delta S. Negative 21 equals 58 minus X minus 9. Solving, X equals 70. The heat of formation of B2 is 70 kilojoules per mole. The key insight, K unlocks delta G, and delta G unlocks the entire thermodynamic chain. 100. 100. Let's dive in. We know that one key number in this thermodynamic data table is unknown, the heat of formation of B2. We're given the equilibrium constant at 500 Kelvin. The goal is to use that information to find the missing enthalpy value. Here's our approach. First, we'll calculate the entropy change for the reaction using the known entropy values in the table. Second, we convert the equilibrium constant into a standard Gibbs free energy using delta G naught equals negative 2.303 times R times the log of K. Finally, we use the fundamental relation delta G equals delta H minus T delta S to solve for the unknown. Let's start with the entropy change. Products minus reactants, 2 times the entropy of AB minus the entropy of A2 minus the entropy of B2. That's 444 minus 146 minus 280. That simplifies to 18 joules per Kelvin per mole. Now we convert K to delta G naught. We know log K equals 2.2, T is 500 Kelvin, and R is 8.3 joules per Kelvin per mole. Plugging in, the result is approximately negative 21 kilojoules per mole. Notice how a large K gives us a strongly negative delta G. The reaction strongly favors products. Next, we express the enthalpy of reaction using Hess's law. 2 times the heat of formation of AB minus that of A2 minus X. That's 58 minus X kilojoules. Substitute into delta G equals delta H minus T delta S. Negative 21 equals 58 minus X minus 9. Solving, X equals 70. The heat of formation of B2 is 70 kilojoules per mole. The key insight, K unlocks delta G, and delta G unlocks the entire thermodynamic chain. Minus 280 words, minus 112 seconds. 5 reactions, 1 chain. And the final product hides 2 nitrogen atoms, not 1. Here's our approach. First, we'll trace each reaction arrow to identify every intermediate. Then we'll pause on the protection-deprotection trick that controls where the second nitro group lands. The key move is recognizing that the final product has 2 distinct nitrogen atoms. Finally, we calculate the percentage using its molecular formula. Benzene reacts with nitric and sulfuric acid at 60 degrees. The acid mixture generates the nitronium ion, which attacks the ring. One hydrogen is replaced by a nitro group. Product P is nitrobenzene, a single nitrogen attached to the ring. Tin in hydrochloric acid at heat reduces that nitro group, all the way down to an amine. After neutralizing the pH, the nitrogen is now a free amino group. Product Q is aniline, aminobenzene. Now let's move on to the next step, the acetylation to form acetanilide. Now, here's the strategic move. We treat aniline with acetic anhydride to cap the amino group as an amide. This is called acetylation, protection. Why protect it? Because in the next step we'll use strong acid, which would protonate a free amine and completely change where the nitro group lands. Product R is acetanilide. Step 4, second nitration, leads to para-nitroacetanilide. With the amine protected as an amide, we run the second nitration. The acetamido group is an ortho-para director. Steric effects at the ortho positions push the new nitro group to the para position. The major product S is para-nitroacetanilide, now carrying 2 nitrogen atoms. The final step hydrolyzes the amide bond. Acid and ethanol at heat cleaves off the acetyl group. Neutralizing the pH frees the amine. Product T is para-nitroaniline. The amino group is restored, and the para-nitro group stays. Para-nitroaniline has the formula C6H6N2O2. Molar mass is 72 plus 6 plus 28 plus 32. That's 138 grams per mole. 2 nitrogens contribute 28. 28 divided by 138 times 100 gives 20.3%. Nearest integer, 20. 2 reactions, same order, identical pre-exponential factors. The only difference? Reaction 1 has a higher energy barrier. Which rate constant wins, and by exactly how much? Here's our approach. First, we write the Arrhenius equation for both reactions. Then, since A1 equals A2, the pre-exponential factors cancel when we form the ratio K2 over K1. Finally, we take the natural log and substitute to get the answer. The Arrhenius equation says K equals A times e raised to the power of negative EA over RT. The exponential factor captures how many molecules have enough energy to cross the activation barrier. For both reactions, we write this out. 1 for K1, 1 for K2. When we divide K2 by K1, the pre-exponential factors cancel since A1 equals A2. We are left with e raised to the quantity EA1 minus EA2 all divided by RT. Since reaction 1 has the higher barrier, K2 over K1 must be greater than 1, which makes physical sense. Paragraph 5, Step 3, ln and calculation. Taking the natural log, ln of K2 over K1 equals the activation energy difference divided by RT. Critical step, convert 20 kilojoules to 20,000 joules, because R is in joules. Then 20,000 divided by 8.3 times 300 gives us 8.03. Rounding to the nearest integer, the answer is 8. Reaction 2 is roughly 3,000 times faster. That is the power of even a 20 kilojoule difference in activation energy. Remember this master formula, ln of K2 over K1 equals delta EA divided by RT.